For as long as we've had digital secrets, our private keys, our data, our identities, we've basically done one thing to protect them. We lock them up. We build these digital fortresses, these hardware security modules, or HSMs, and we make them as tough as possible. But what if that's the problem? What if the vault itself, the very act of storing a secret, is the biggest flaw in the whole system?
I mean, you have to ask, right? If our digital vaults are so secure, why do they keep failing? Why do we keep seeing these catastrophic breaches where, poof, the entire kingdom is gone in an instant? Well, the answer isn't that we need stronger walls. It's a deep paradox in the way we've been thinking about security for decades.
Okay, so let's break this down. On one side, you've got the vault, your HSM. It's this centralized fortress, which sounds great, but what it really becomes is a giant, glowing honeypot. It's the one place an attacker needs to hit. Then you look at the threats, things like confused deputy attacks, where a perfectly legitimate program gets tricked into using its authority to steal data for the bad guys. The fundamental problem is you have this one static, unchanging secret guarding all this data that can be copied in a nanosecond. If that vault gets cracked, it is absolutely game over.
So if building bigger, stronger vaults isn't working, where do we go from here? Well, we have to think completely differently. We need a new philosophy, one that's kind of radical. It's this idea of finding security not through presence, but through absence.
And it all boils down to this one simple, powerful mantra: nothing stored, nothing to steal. It completely flips the script. Instead of building better walls to guard a treasure, what if we designed a system where there's just no treasure to guard in the first place?
And this is what it looks like in practice. It's called the Zero Material Protocol, or ZMP. The core idea is that cryptographic keys are never ever stored at rest. They don't live on a hard drive, they don't live in memory. Instead, they are literally materialized or crystallized into existence for one specific job, used for just a few milliseconds, and then they completely evaporate, leaving zero trace that they were ever there.
You know, this really marks a huge shift in how we think about access. Old-school security is like a bouncer at a club door asking, "Who are you?" It's all based on identity. But hey, IDs can be stolen or faked. This new model is different. It's capability-based. It's like having a single-use ticket for a specific movie. The system doesn't care who you are. It just asks, what do you hold? If you have the ticket, you're in. And once the show's over, that ticket is just a worthless piece of paper.
Okay, this all sounds great, but it probably leaves you with one massive question. If you're not storing the key anywhere, where in the world does it come from? How do you just create it out of thin air? Well, the answer isn't in software. It's in the physical hardware itself.
The technology is called a physically unclonable function, or a PUF. And honestly, the best way to think about it is like a fingerprint for a microchip. Because of tiny, random imperfections during manufacturing, every single chip is physically unique. A PUF is a way to harness that uniqueness to generate a consistent secret response. It's not a secret written down somewhere, it's an intrinsic property of the silicon, a unique, unclonable hardware scent.
So the system isn't a vault pulling a key off a shelf, it's a forge. It's creating a brand new key from raw material every single time, using the unique physics of something like graphene oxide. And here's the real game changer. You don't need to replace your entire CPU for this. It's an additive component. You can just add a graphene-based PUF chip to your existing setup. This makes it a dramatically lower-cost evolution of those big, expensive traditional HSMs.
So check out how fast this all happens in what's called the crystallization cycle. Step 1, a request comes in holding a valid token. Step 2, instantly the hardware's unique fingerprint is used to materialize a key in a secure little bubble of memory. Step 3, the key does its one job and only one job, like decrypting a block of data. And then step 4, the moment it's done, that memory bubble is scrubbed, wiped, and zeroed out 3 times over. And poof, it's gone. The entire life cycle, start to finish, takes milliseconds.
Now, this architecture also solves one of the oldest, scariest problems in all of hardware security, the ghost in the machine, if you will, the risk of manufacturer backdoors. How can you ever truly be sure that the company that made the chip didn't keep a spare key for themselves? See, the problem starts right at the factory. The very first secrets loaded onto a device to get it started, its birth secrets, can be its most permanent weakness. Because if the manufacturer knows that initial state, they could potentially have a backdoor into that device forever.
In this system, that original secret is called the initial pepper. You can think of it as the cryptographic scaffolding used to construct the device's security. It's absolutely essential to get the whole thing built, but if you just leave that scaffolding up after the fact, it becomes a huge, glaring vulnerability.
And that's where the secure erase transition comes in. It's a critical, one-way process. Once the device is deployed, it generates its own new, unique production keys. Then, it permanently purges that initial pepper and completely wipes the original factory bootloader. It is literally burning the scaffolding and destroying the blueprints, forever severing the link to its own creator. The device becomes truly sovereign.
This process is so thorough that it makes the device factory immune by closing 3 critical security gaps. The forensic gap: even if you do a deep silicon-level scan, you find absolutely nothing of the original secrets. The binary gap: the original software needed to recreate that factory state is just gone. And the physical gap: if you try to physically tamper with the chip during the erase to see what's happening, it'll just fail and brick itself. There is no going back.
So when you put all of these pieces together, what do you get? What does this all add up to? Well, it points to a future for security that is stateless, truly sovereign, and just incredibly resilient in a way we haven't seen before.
This kind of architecture achieves its immunity through 5 pillars that all work together. It's zero material, so there are no keys to steal. It's stateless, so there's no transaction history to attack. It's unclonable because its security is literally fused with its physical hardware. It's self-authenticating, so it doesn't rely on a vulnerable identity system. And finally, it's factory immune, cutting all ties to its creator. When you combine them, you get a system that just doesn't have the attack surfaces we've been fighting against for years.
And this quote really drives the point home. Imagine the worst-case scenario. Somebody kicks down the door and physically seizes the server. What do they get for their trouble? Nothing. Just a bunch of useless, encrypted blocks of data and a vacuum where the keys should have been. But of course, they never were.
And that brings us to the final thought-provoking question that this entire architecture is built around, a question that might just change how we think about security forever. If the key never really existed in the first place, what is there left to steal?